Hello and welcome to the third and final lecture on the very popular and very common building material that we call aggregates, or crushed rock and small particles of rock which together can form a bulk. This is going to be a shorter lecture than the first two parts. Last lecture we talked about strength of aggregates, and we talked about strength not of a rock as in an individual particle of an aggregate, but actually the bulk of lots of different stones or rocks and their strength. And if you remember correctly, we talked about how aggregates can have a lot of strength in compression and also in shear, but they have next to no strength or zero strength in tension, because of course the particles are not being pushed or squeezed together, they're being pulled apart. And unless there is a glue, something like cement or bitumen, which is making the parts of the aggregate stick together, then the particles are just going to pull apart as soon as you place any kind of tensile strength. If I have two little stones and I'm pushing them together between my fingers, I can squeeze them and squeeze them, but if I actually pull them apart with my two hands, it's not going to take any strength whatsoever. There's nothing holding the two stones together. So we talked about strength. We also talked about size of aggregates, and basically we talked about how the smaller the size of an aggregate particle, the stronger it is. And the reason for that is there's less air voids, and air gives no strength to an aggregate. So that's why we always use very small particle aggregates. If we're building something such as a building foundation, we compress it and we make it very small so that there's no air voids. That gives it good strength. We also talked at length about grading, how aggregates can actually be well graded, poorly graded, or gap graded, and that has to do with the range of sizes of particles found within an aggregate. And we talked about how, again, well graded, gap graded, they have a very low void content, so they can have more strength, whereas poorly graded, uniformly graded, that has very low strength because it has a very high void content. Now, that doesn't mean we always want it well graded or gap graded, although we often do. Poorly graded, uniformly graded does have an advantage in that where you want lots of void content so that water can pass through for something such as a drainage ditch or a wastewater treatment facility where the sewage needs to pass through the rocks, then you would want uniformly graded. We also talked just briefly about how uniformly graded aggregate has the advantage that it can actually be self-compacting. So if you needed to fill a big hole and you can't put a compactor or roller down in the hole, you would use uniformly graded. But today we're going to be talking about some other properties of aggregates. The first property we're going to be talking about is particle shape. Now, obviously, all the particles inside an aggregate, they have a variety of different shapes. Now, if the particles are too spherical, if they're very spherical, that will mean they will have less surface area. Now that should be quite obvious to you. Spheres have a much lower surface area for a given volume than, say, a cube. So the more rounded or circular an aggregate is, the lower the surface area. Now why should that matter to us? Well, if we are going to use the aggregate in something as a concrete or an asphalt, we want to be sticking all of the aggregate particles together with cement or bitumen in the case of asphalt. Now, if there's less surface area, then obviously they're not going to stick as well together. And that's why, if you're making a concrete, it is preferable to have angular and more cubically shaped aggregate than rounded aggregate. Now, rounded aggregate, an example of rounded aggregate would be river gravel. So this is a picture of river gravel here, and you can see all of the particles there. They're actually very circular. They're smooth and they're rounded because the water in the river has smoothed off all the rough edges with erosion. Now, river gravel does have a lot of aesthetic qualities. That's why it's very popular for gardens. It usually has lots of different colours inside it. It's also really nice for walking on. You can walk on river gravel barefoot and it doesn't hurt your feet the same way crushed rock would. But it's a very popular aggregate to use for concrete here in Kurdistan. And the weakness of that, and the reason why sometimes concrete fails and breaks in Kurdistan, is it does have a lower surface area. And so obviously it can break out of the cement and the concrete cracks and fails easier than if the concrete was made with a crushed rock aggregate. Now, the other thing with rounded aggregate, if it's from a river gravel, sometimes it's easier to get uniformly graded. You don't need to necessarily put it through a sieve. The way that rivers work, rivers will carry away all of the smaller rock, all of the smaller aggregates with the river flow, and they will leave aggregates that are all about the same size on a riverbed. So you can actually harvest that and you will find that all of the rocks are a similar size. And that's caused by a phenomena called river armoring, if you want to look that up. So you can see in that picture there with the river gravel, basically all of those rocks, they're roughly about the same size, aren't they? It's uniformly graded. So with particle shape, it can actually influence the strength of the aggregate too. So look at these particles here on the right. They're really flat and elongated, and they're kind of flaky, aren't they? We would call this flaky aggregate. They're all little flat pellets, if you like. Now, if you were going to lay out that aggregate as a foundation for building a house, let's say, it's actually going to have a very low compressive strength. Even if it's a very strong particle, it's going to have a low compressive strength in the combined bulk aggregate. The reason for that is because of the shape of the particle, there's going to be a lot more voids. The percentage of the aggregate, which is air, if you were going to fill a bucket with this aggregate, half the bucket will probably just be air, won't it? Because of the way these flaky aggregate particles align themselves, they will leave very large cavities in between them. Now that air doesn't give any strength whatsoever. The higher the void content, the higher the void ratio, the lower the overall compressive strength. The other thing with flaky aggregate is that if you are using this to make a concrete or an asphalt, let's say, then you're going to need to fill those voids. Just as if you had a uniformly graded aggregate, you're going to need to fill those voids with cement or with asphalt, with bitumen. and that's really expensive. You do not want that. And that's why it's important that the aggregate that we use for making concrete is not overly flaky in shape. We want the aggregate to be sort of cubical in shape, more or less. Now, what sort of aggregate, what sort of rock would it potentially break into these flaky particles when you make it into an aggregate at the quarry? Well, it's sedimentary rock. You're going to learn about this in Introduction to Geology for Engineers with Mr. Varajan. But basically, sedimentary rock, it's been compressed into layers of minerals called strata. And so when you break it with a rock crusher, it actually forms these flaky cornflakes, depending on the type of sedimentary rock. So sedimentary rocks like shale, sandstone, slate, if they have a low strength between the strata, these sort of layers between of sheeting of minerals, then when you put it through a rock crusher, the aggregate particles will be flaky in this sort of shape. And we really have no use for flaky aggregate in civil engineering. It creates a high void ratio, which lowers the strength, and it also makes concrete much more expensive to manufacture because you need more cement, and it lowers the strength of the concrete too. So, how do we ensure that an aggregate is not overly flaky? Well, what we do is we do something called a flakiness index. So a flakiness gauge, like the one you see on the right, we will do this when we do eventually get back to the laboratory. You do this as part of the sieve analysis. What you do is you collect all of the aggregate particles that landed in, let's say, the 9.5 millimeter sieve, and then you would be trying to see how many of those aggregates would fit through the 10 to 6.3 millimeter opening on the flakiness index. So that's the smallest one there. And you will weigh what proportion will fit through it, and you will weigh the overall aggregate. Now, you will only do this for particles larger than 6.5 millimeters, but basically a rule that comes from the British standards and American standards, that if you're making concrete, the coarse aggregate, the larger size aggregate, that should not have a flakiness of more than 40%. 40% by weight of the aggregate should not be able to fit through that key with the flakiness gauge for the given sizes. Now, I will post a video of a flakiness index test online, so you will have a better idea of how it works. Again, if you've got questions about this, I'm available in the Zoom tutorial or anytime during the work week by phone or by email. Now, another property of aggregates that we need to look at is degradation, resistance, and hardness. Remember, we talked about how porosity is often a reason why aggregates will degrade. They will break apart. Well, they can actually break apart for another reason, and this is called scratching and brittleness and rubbing, effectively abrasion, friction. That is the mechanical wearing and scraping of rock surfaces. So, this is a big problem for aggregates that are being used for road surfaces, let's say, because a road surface is being used for cars to drive on. So you will have cars with their tyres, hundreds of cars driving over the surface for every hour of every day. And that constant abrasion or friction can actually wear down and smooth the aggregate particles inside the road surface. So maybe you've noticed this driving around certain roads in Kurdistan. Occasionally the road, especially where the tyres of the car are driving, after a while, if the road is kind of old, it will go kind of smooth. It will be a smooth surface just where the tyres are constantly driving on it. And that's basically the aggregates inside the tar seal, the road surface, wearing down. They're being smoothed flat. And basically, eventually the road will wear out, it will get cracks in it, and you have to remake it. Well, hardness is not a measure of how strong a particle is. It's not a measure of how much strength or force an aggregate can withstand. Hardness is actually about how resistant an aggregate is to abrasion and deformation and brittleness, if you like. So, remember in the very first lecture of this class, we talked about how in the Bronze Age, the people used to make bronze by mixing copper and tin together. Copper was a very strong metal, but tin was a very hard metal. And by combining them together, you got bronze, and you had a hard and strong material to use. It needed to be strong so it wouldn't break. If you were making a bronze spear, for example, it needed to be strong so it wouldn't break. It also needed to be hard so it would be very sharp, and it wouldn't go blunt in time. Now, if an aggregate is prone to abrasion, it will deform easily, and really it's not suitable for anything we use in civil engineering. The reason for that is civil engineering, we're building things that need to last a long time, 10, 20, 30, 100 years, and so we need it to be a very stable aggregate. How do we measure abrasion? Well, effectively we do this by the Los Angeles test. Now, the Los Angeles test is where we take a sample of the aggregate and we weigh it, and we ensure that this aggregate, all of the particles are bigger than, let's say, 5 millimeters in diameter. Let's say, just for example, there's different tests you can do. You place that sample that you've just weighed inside that big blue drum there. This is called a Los Angeles test apparatus. It was developed in Los Angeles many years ago. And then inside the drum you would also place 12 steel balls. These steel balls weigh about 1 kilogram each, and they're about the size of a snooker table ball. And then you close the hatch where you can see that label, U-test, you tighten it, and then you turn the drum on, and it will basically spin for 500 revolutions. And what will be happening is these steel balls will be pounding into the aggregate like that. And they'll do this for maybe 20 minutes, and they will be pounding the aggregate into dust. After you've done this, you weigh the aggregate again after you put it through a sieve, and all of the dust that has been made is blown away, it falls through, and you weigh it again. And you take the percentage of aggregate that wasn't broken down. I'm going to show you a video now. Now, I've got this on this lecture, but I actually do not know if it's going to show. If it doesn't, if the next slide is just a wide screen, don't worry, I'll also put the video of this Los Angeles test directly onto Moodle. So there you're going to see it for testing hardness. So here we go.
In this video, we are going
so
to
this is a Los Angeles test,
which is a measure of an aggregate's strength, or more precisely, its resistance to fragmentation.
Okay, so this is a test that is done by a company in Britain. So the principle of hardness is determined by the Los Angeles test. First, you get your sample of aggregate. It's 5 kilograms. That was placed in
the degree of degradation is measured by using a 1.6.
It's hard without the narrator. But what they've done, they've taken the sample and they've put it in a sieve. They've shaken it, or they've washed away all of the smaller particles, and then they've placed it in that drum with the 12 balls. So here they are preparing the sample. You've got a sample that's being delivered to the lab. It's a bag of about 15 kilos of the aggregate. And you do the sieve test. Normally this is done in association with the sieve test. When a company comes to a lab and they tell you to analyze an aggregate, normally you will do a sieve test, flakiness test, and hardness test, Los Angeles test, all at once. So you shake it, and then the sample that is larger than, I think, 1.6 millimeters, you wash away all the dirt, all the dust, and then you dry it in the oven. It has to be very dry, so you end up with a fairly uniform aggregate. Now you weigh it. So they've weighed it at being 5 kilos. They've placed it in the drum with the 12 balls. This is safety equipment. We don't actually have this in our lab at the University of Kurdistan, but you should know that this is a very loud experiment. It really is. It's quite a lot of banging. And so here they've actually got a room that they enclose so that no one's getting their ears damaged. They turn it on, and what they're doing is they're spinning it, and it will be spinning for 500 revolutions. Very noisy, this.
Each ball must have a diameter of between 45 and 49 millimeters and a mass of between 400 and 445 grams.
So those balls are falling around and they're pounding into the aggregate, and some of the aggregate particles are, from the friction, just having some abrasion and dust is breaking off them, or they could be brittle and they could be sort of snapping in half. You're trying to see how much smaller, what proportion of the aggregate will now be smaller than 1.6 millimeters. There's a few different tests you can do with this. They're all in the standards, ASTM American standards and British standards, but yeah, we will do a test in the lab when we do eventually get back to the university. So they've spilt out the aggregate in the 12 balls there, and have a look at that. Look at the aggregate there. Suddenly there's a lot more dust, isn't there? That wasn't there before. That's because the balls have rubbed and caused friction, and a lot of the dust has washed away. So now we're going to just wash it, get all the dust out. We're going to place the aggregate back into the oven to dry it out. All the dust has been removed, and we're weighing it again, and look, suddenly it's only 4.2 kilograms. It's lost a lot of weight in dust. So the Los Angeles test is basically just trying to find a ratio. You take the original weight, you minus the final weight, and then you divide it by the original weight again, and then you multiply it by 100 to get a percentage. So the Los Angeles test here is 16%. That means that 16% of the aggregate has turned into dust. And you can find all this out on the British Standard, that number just there. If you do a Google search there, you can find the procedure. I hope that was helpful. If you couldn't see this, if the video didn't show, just know that I'll put this video on Moodle too. Okay. Final slide here. You've got everything you need to do assignment 2. This is the assignment on aggregates. It's available on Moodle and it's due at 12 p.m. on the 17th of May. So if you're watching this in the middle of April, you've got plenty of time, but I recommend you get ahead of the game. Now, if you have any questions on this, please let me know. I'm available on phone and email anytime. By the way, with the assignment, okay, never mind that. The assignment is due 17th of May, 12 p.m, so middle of the day. You should be able to submit it to me by email. Final thing, if none of this has been clear to you, or you want to read more about aggregate because you find it so fascinating, there's a really good book called Civil Engineering Materials by Somayaji. Now, obviously, we can't go to the library. It's available in the library at the university. But if you want, you can buy this book on Kindle. I think it'll cost you about $20. And it's an excellent book to have as a resource throughout your career as an engineer. If you read pages 35 to 67, that's what you need to know for this course, this module. But of course, all the relevant information has been given to you in the lecture as well. Thank you and goodbye.